Problem number 13. A mass is attached to the wall by a spring of constant K. When the spring is at its natural length, the mass is given a certain initial velocity, resulting in oscillations of amplitude big A. If the spring is replaced by a spring of constant 2K and the mass is given the same initial velocity, what is the amplitude of the resulting oscillation? So during oscillation with the mass and the spring, we have kinetic energy going to potential energy of the spring and backward. So if we're giving initial kick to mass, all this kinetic energy going to potential energy of this spring with constant K, and we have this formula. If we replace now spring with a constant 2K, we have the same kinetic energy from mass, and it's equal to potential energy for new spring. That's this one. Now we can equalize both parts and have this equation. The result is this one. New amplitude A1 equal 1 over root 2 old amplitude A, which is answer B, this one. Problem number 14. A space-borne energy storage device consists of two equal masses connected by a tether and rotating about their center of mass. Additional energy is stored by a reeling in the tether. No external forces are applied. Initially, the device has kinetic energy E and rotates at angular velocity omega. Energy is added until the device rotates at angular velocity 2 omega. What is the new kinetic energy of the device? So first of all, we can write equation for kinetic energy. So kinetic energy equal 1/2 moment of inertia multiplied by omega square. If we notice that angular moment equal this expression, we can rewrite kinetic energy in form of this one. Now we see that angular momentum is constant because we don't have any external forces, and according to this formula, if we increase omega twice, we have kinetic energy increased twice. So the result is B. Kinetic energy equal 2E. Problem number 15. A uniform round tabletop of diameter 4 meters and mass 50 kg rests on a massless, evenly spaced legs of length 1 meter and spacing 3 meters. A carpenter sits on the edge of the table. What is the maximum mass of the carpenter such that the table remains upright? Assume that the force exerted by the carpenter on the table is vertical and at the edge of the table. So first of all, we have to realize that we have equilibrium around this right leg of this table. So if a carpenter has a too big mass, it starts to rotate around this point. So it means that we need to check what is the torques created by carpenter and the table around this axis of rotation. So first of all, let's check what is the our notation. Suppose that a mass m1, that's the mass of a table, mass m2, that's mass of carpenter, still unknown. The distance between center of mass of table and right leg is 1.5 meters, and distance from carpenter and right leg is 0.5 meters. So now we can write equilibrium equation for this system. Table creates counterclockwise torque, which is L1M1G, and carpenter creates clockwise torque, which is L2M2G. Finally, we have this expression: M2 equal L1 over L2 M1, and when we put numbers, we have maximum possible mass of carpenter is 150 kg, which is answer D.